I'm Amudha. I'm working as assistant professor in the Department of Computer Science Engineering, Bharat Institute of Higher Education and Research. Today's course we're going to see is Design and Analysis of Algorithm. The course code is U18Pccs402, and the topic we're going to see in today's session is an abstract problem using dynamic programming. So in today's session we're going to see what is dynamic programming and what are the main properties of dynamic programming and why we use dynamic programming, why we are not going for with the help of the greedy method. Yep. So we'll see what is dynamic programming. Dynamic programming is a method is obviously used for solving optimization problem. So what do you mean by optimization? Which means that so when I give you guys to solve a problem and each one will be solving in a different way, but at the end, the one which takes less time and which gives the best solution will be taken. So that is the optimization. Okay. So in dynamic programming method, we solve using the optimization method, which means that we solve optimization problems. The basic idea behind the dynamic programming is we compute the solution to the subproblems once and then we store the solution in a table so that can be reused whenever we require. This is very simple. So when a problem is given, you're dividing a problem, which means that you're dividing a problem into subproblems, you're solving those subproblems and that data has been stored in a table. So whenever you need it, you will be referring from the table. And this dynamic programming approach is also called as a bottom-up approach. And this dynamic programming term was coined by Richard Bellman, who described the way of solving problems, so which always finds the best decision among the available decision. And we'll see the what are the two major properties of dynamic programming. So always the dynamic programming will be solved using these two properties, that is called the overlapping subproblems and the optimal substructure. So we'll see what is what. So when I explain you guys with an example, that will be clear understanding for you people. Now, the steps for dynamic programming approach. Dynamic programming algorithm is designed using the following four steps. So what are those? We'll see. Okay. And see, we characterize the structure of an optimal solution. This is the first step. So always we'll getting the structure in which way, in which format, what we gonna do. So we characterize the structure of the optimal solution. Next, so recursively define the value of an optimal solution. So recursively. So we are defining it again and again, so which means that when we use it again and again, that is called the recursive function. So we are recursively defining the value of an optimal solution. The next at the third step is we compute the value of an optimal solution, which means that by means of a bottom-up way. See, this dynamic programming, we are dividing a given problem into subproblems. We are solving individual subproblems. Then we'll be choosing the one which is the best one, which is the optimal. So we are computing the value of an optimal solution in the bottom-up fashion. The final step. So here we construct an optimal solution from the computed information. Okay. So this is the final step. So at the end, we'll get a solution which is optimal. So now we're going to see example for dynamic programming. So before seeing with examples, we'll see what are the applications. Okay. So the major applications of dynamic programming are so matrix string multiplication, longest to common subsequence, traveling salesman problem, then abstract problem. So matrix string multiplication. So here, that is an easiest way of solving the matrix string multiplication. Okay, so that also will be solved using the dynamic programming method. Next is longest to common subsequences. This concept is like when a strings or two or three strings are given. So among that, I'm identifying which forms the largest sequence of strings. Okay, so this is the longest to common subsequence. So from the given two strings, will be identifying which is the longest to common sequence present from the given string. So by approaching using a dynamic programming method, we'll be getting the strings from the given string. That is called longest to common subsequence. Next is the traveling salesman problem. So traveling salesman problem, here a number of cities will be given. Then you will be choosing a city, which means that you have to start from a city, then you have to end in a city in between. You have to visit all the cities from the source or the starting city, then visit all the other cities only once with the minimum cost, and then you have to come back to the destination city. Yep. So the starting and the ending should be the same, and the cities, rest of the cities, you have to visit only once with the minimum cost. This is called traveling salesman problem. Next is knapsack problem. So this is the problem we're gonna see. So we're gonna solve this problem using a dynamic programming. So the concept of knapsack problem is, so a bag will be given, n number of items will be given along with the profit. We have to place an objects one by one in the knapsack, so that you have to choose the objects with the maximum profit and the minimum weight. Okay, so we'll see. So the 0 bar 1 knapsack problem is also called as rucksack problem. We'll see what are the major thing and what is explained in the knapsack problem. So see here, so given statement for the knapsack problem is a set n of items. So n number of items will be given in which I will be having. So each object will have the weight and the profit. It's called value or a benefit. So objects will be given. So each n number of objects will be given, and each objects will have a weight and the profit. Suppose if I'm giving you guys a four objects and I'm giving you a bag. So for each object one, object two, object three, and object four, each object will have a weight and then will have a profit. So your target is now you have to choose an object one by one. You have to put in the knapsack, which means the capacity of the knapsack also will be given. Suppose if the capacity of knapsack I am giving is only 10, so you can insert an object of weight till 10. You should not exceed beyond 10. Okay, but the profit should be maximum. So see here, this is a given condition. So which means that n number of items will be given. For each item, we'll have the positive weight and then we'll have the positive value or the benefit. So what is the goal? So what we gonna do? So the goal is we have to choose an item with the maximum total benefit, but with the weight at the most, which means that the capacity of knapsack. So in this case, we have to make the objective and the constraint. So objective is to we have to maximize the profit, that is called benefit, and the constraint is that the weight of the objects that is going to be inserted in the knapsack should be less than the capacity of knapsack. Okay, this is the goal. So you guys are clear? So see here, so the knapsack problem is the concept is n number of objects will be given and each objects will have weight and the value or benefit. So the goal is to we have to place one by one object in the knapsack, which means that the capacity should be less than the knapsack capacity and the profit should be maximum. That is what the objective is, to maximize the profit, and the constraint is to we have to minimize the weight or we should not exceed the bag capacity. Next, then why we cannot solve using greedy method? So this greedy approach provides the optimal solution to the fractional knapsack only. And the 0 to 1 knapsack cannot be solved by greedy approach. Why? Because it does not give you an optimal solution when you solve this 0 to 1 knapsack problem. So we'll see an example. We will be solved using a greedy method, and why so? Why we are not able to solve using greedy method? To see this example, see the capacity of bag given is 200. Okay, and the items are, I have given four objects. So x1 is one object, x2 is one object, x3 is one object, x4 is one object. So x1 object profit is 12 and the weight is 50. X2 object is profit is 10, weight is 55. And x3's object is profit by weight ratio is 8 and the weight is 10. And the next four object or the fourth object is profit by weight ratio is 6 and the weight is 100. So here what value of greedy we have to identify. Normally how we, whenever we solve using greedy method, we will multiply with the profit by weight ratio into the weight. So 50 into 12 plus 55 into 10 plus 8 into 10. So when we add all those things by means of a greedy method, we get 1230. But if I try to get an optimal value, so how I will solve using optimal value? I'll always take the one with the minimum of a profit weight ratio. So when I see, when the compared with the objects of object 1, 2, 3 and 4, the object 4 profit by weight ratio is 6. So I'm taking 6 into 100. So the weight is 100. Okay, into 6. Next. Next, which is the next least having the profit by weight ratio is 10. So I'm going with the 10 into 55. Okay. So next profit by weight ratio is 8. So 8 into weight is 10. So when I add these 1430 I'm getting, which means that the profit. So this is more. So that's why we are not going with the greedy method. We go with the dynamic programming method. So this is a basic example for understanding why we go for dynamic programming method and why we are not going for greedy method. Which means that in greedy method we are not getting the optimal solution. Okay. Yes. So, this is the reason we always go with the dynamic programming method, not with the greedy method. Why? Because in greedy method, we will not get the optimal solution. But when we go with the dynamic programming, we will get the optimal solution. So, we'll see a detailed example of an abstract problem. Okay. So see here, so the greedy approach does not ensure an optimal solution to the 0 to 1 abstract problem, but to solve the 0 to 1 abstract problem, we use dynamic programming approach. So these are all the recursive formula or the procedures for solving the subproblem using dynamic programming. We use three cases. The first is the no items in the knapsack or the weight of the knapsack will be 0 and the profit is also 0. So we have to solve using the subproblems with the three recursive formula. The three cases, we're going with the first case. The first is that if there are no items in the knapsack, so the weight of the knapsack is 0. So and the benefit or the profit of the knapsack is also 0. Next, the second case. Suppose the weight of an item exceeds the weight of a knapsack item, then that cannot be included in the knapsack. So see here, the weight of an object is more than the weight of the knapsack capacity, then the object cannot be included in the knapsack. So the maximum benefit will be V, which means that the V will be solving this using the table method. So V of the previous objects, comma, the current weight will be considering that. Okay, next. Third case, suppose the benefit is the maximum achieved by either not including the item, which means that if it is maximum, we are not including the item, then we will be taking the previous value weight or we will be adding the one with the previous value with the next new weight along with the previous weight. So you'll understand when we solve using this with the example. See here the formula is V of I comma W is equal to if the knapsack capacity is 0 and no object in the knapsack, the value is 0. Suppose if the weight of this current item is greater than the capacity of knapsack, then we are taking the previous value object or the previous value weight. That is V of I minus 1 comma W, which means that the weight will be the same. Will be taking the value from the previous row or previous column. Next, suppose if not both the cases, if the value is less, if the weight of an object is less than the weight of the knapsack is less, then what we have to do, we have to choose the one which is maximum between the two, the current object and the object with the previous one along with the object added present in the knapsack. You will be checking and choosing the one which is the best. That will be considered and that will be added into the knapsack. These are all the three cases. Okay, so now we are going with an algorithm. So far, what we have seen is the algorithm, and this is the way we're gonna solve. So We guys have to understand these steps clearly. When you're clear with these steps, and this step will be repeated for each and every column, every rows. When you check with the profit and the weight of an object, and then you will be inserting into the knapsack. So see here, 0 to 1 knapsack algorithm. So first initially, we are initializing the first row to 0. So for W equal to 0 to W, which means that 0th object in the weight of capacity of a knapsack. If that is 0, initially all the values will be 0. That is V of 0 comma W is equal to 0, which means that the first row will be 0. Next, we are making the first column equal to 0. Suppose if for I equal to 1 to n, so V of I comma 0 is equal to 0, which means that in the table, we are starting the values from 0. So the 0th row and the 0th column will be 0, 0, 0, which means that you will not insert any object into the knapsack, then the value will be 0 only. Next, for I equal to 1 to n, suppose you are in the first row. So what do you have to do? You are in the first row, then you are checking for the weight. If that weight is 0, that is from 0 to the capacity of knapsack, then you are checking. You remember the three cases we have seen? Now we are doing with the first case. Okay. So we are checking. This is the algorithm for the knapsack problem. So initially, we are making the rows and the column to 0, and then we are going for the first object. So when you go for the first object for I equal to 1 to n, so for W equal to 0 to W, which means that we are starting from the weight 0 till the capacity of the knapsack. So then we are checking, and you guys remember with the three cases that the second case we are going with this. So going with this W of I, which means that the first object weight is less than or equal to the knapsack capacity, then the item will be added as a part of a solution. So what is the procedure to add? So now we'll take the value, along with that we'll take the thing which is in the previous row, previous column, then we'll compare if that is greater, then that will be considered as an updated weight of the knapsack and that object will be inserted. Suppose if that is not greater, so that current weight is kept and that will be obtained from the previous column, that will be considered as the weight, and this object will be inserted into the knapsack. Suppose even if this is not satisfied, if the if else fails, what happens? We'll go with the else. What we'll do will be inserting the previous object into the knapsack. We'll see with a step-by-step process. So see our example. So this is the example. We have four number of elements and the maximum weight is 5, which means that the knapsack capacity is 5. So whenever I insert an object in the knapsack, when I add all those weight, it should not exceed 5 value. Okay. So now elements in the knapsacks are given along with the profit and the weight. So the first element profit is 2 and the weight is 3. The second element object is so weight is 3, profit is 4. And the third element object is the weight is 4 and profit is 5. And the next object is profit is 6 and the weight is 5. So we have got 4 objects. So we'll be solving. I said dynamic programming will be solving and that result will be stored in a table. And whenever we need that data, we'll be retrieving from the table. Yeah. So this is the table. As of now, I said we have got 4 elements. So I'm just drawing a table with the 4 rows and the 5 columns. And then I'm adding because the object I have is 4. So I'm taking I equal to 0, 1, 2, 3, and 4. That is represents my row. And what is the capacity of knapsack given? It is given as 5. So what I'm doing is 0, 1, 2, 3, 4, and 5. So I'm making 6 columns. This is the way how we represent in a table format. So now the first case, I is W, I is 0, W is also 0. So obviously what we have to do, so we are making the all the rows to 0, all the first column and the first row we are making it as 0. So see here, so W is equal to 0, then W, then what we are placing is we are making that row as a 0. So V of 0 comma W, which means that if W is equal to 0, So obviously I equal to 0. Then so V of 0 comma W. So 0 comma 1 will be 0, 0 comma 2 is also 0, 0 comma 3 is 0, 0 comma 4 is 0, 0 comma 5 is 0. So this is how we make the first row in the table as 0. So next step we are making the first column to be 0. Why? Because initially we are not adding any object, so no object will be in the knapsack, and the capacity in the of the knapsack also will be 0 because no object the knapsack. So the knapsack is empty. So we are making, so for I equal to 1 to n. So if I equal to 1, so V of I comma 0 equal to 0. So here V of I comma W. So that is always 0. So what happens if I equal to 1, W is equal to 0. I equal to 2, W is equal to 0 is 0. If I equal to 3, W equal to 0 is 0. I equal to 4, W equal to 0 is 0. So we are making column, first column, all the entries to be 0. Clear? Now we are entering into the major part, which means is the second part. So I said we have three cases. The first cases is making the first row and the first column to be 0. The next. So next is we are going with the first object with the first weight. Suppose the items are listed above, see 1, 2, 3 and 4. The first object weight is 2, profit is 3. Second object is weight is 3, profit is 4. Third object is weight is 4, profit 5. Fourth object is weight is 5, profit is 6. And what is the capacity of knapsack is only 5. Okay. So see clear. I'm starting with the first. So I equal to 1 and W equal to 1. So I have to place in the 1 comma 1 place. So you know in which place I'm going to place this entry for the calculate result. Where I'm going to place. So I equal to 1. If I take the first object, what is the profit? Profit is 3. And what is the weight? Weight is 2. So what I am doing is now I'm currently checking. Okay. So I am checking whether the previous any other object is inside the abstract. No. Then I have to check. I will be checking with the previous column. So when I see in the previous column is 0. So I'm just making that as to be 0. Next, I'm going to the next place. So if I take the same weight is 2, I'm in the same object only. Okay, I'm I equal to 1. I'm having the same object, but the weight is 2. So in the place of weight 2, what is the profit? The profit is 3. So what I have to do is, I will be adding the 3 with the previous diagonal. 0 plus 3 is 3. I'm placing it as 3 there. So next, again I am checking whether I can place any other object or not. I'm again checking. I'm checking with the previous row column value. Oh, and then I'm making it as to be 3. In the next also 4 place also I'm placing it as 3. Why? Because I'm not inserting any other object. Inside the knapsack, I have placed an object 1 and the weight is 3. So that column will be, that row will be 3, 3, 3 only. Clear? Next. So first object I have been inserted into the knapsack. So next, I'm going with the second object. If I go with the second object, I equal to 2, what is my profit? Profit is 4. So what I have to do, I have to place the object only in the 2 comma 4 place, not anywhere between. So what I have to do, I have to mark it as 0 and then I have to copy the same values from the previous row. You guys getting it? The same values from the previous row. Okay, I'm adding it to the next. So in the weight 3, already I have an object of weight 3. Okay, now I'm adding an object of weight 4. So 4 plus 3, 7. So what I'm doing, I'm adding. So 4 plus 3, the diagonal 3 is 3. So 4 plus 3 is 7. I'm placing in text. The next is 4. So next is also 4. The next place I'm adding. So when I add and place, the profit is 7. The capacity is 5. So you guys can cross check. If I place a 7 and when I add the profit, 3 plus 4 is 7 and the weight 2 plus 3 is 5. So that will be placed in the W5 position. Clear. So next, I'm adding a third object. Again, I'm checking. So if I check with all those things, That doesn't mean that does not satisfy. So what I'm doing, I'm taking the values from the previous row. So next, I'm checking with the weight. So whenever I insert a fourth object, the profit is 5. So I'm adding it back with a 0 and placing it to 5. Same. So no other option. I cannot insert beyond 5. So I'm adding only the capacity 7. Profit 7. Same wise, I'm copying from the previous table and then I'm placing it. So at the end, I've got, so I filled this table, which means that I've checked by placing the item 1, 2, 3, 4 inside the knapsack and I have filled it, which means that the maximum profit is 7. So see here, the maximum possible that can be carried out inside the knapsack, the profit is only 7. But now I have to identify what are the object has been inserted in the knapsack. So I have a separate procedure for this. So I have to trace back. How? So see here, this is the trace back for finding the value given in the kept in the knapsack. So this is an algorithm. So see here, all the information we need are present in the table. So now V of n comma w is the maximum value of an item that can be placed in the knapsack. Suppose if I equal to n, then k is equal to w, then we are checking. If that is not equal, then we are making that item as a one we have been inserted in the knapsack. Suppose if the element present in the current row is equal to the element present in the previous row, then this object is already been inserted. So we'll be going to the previous object and we'll be checking that row with the element in the previous row. If that doesn't matches, what we'll do, that object has been inserted, we'll be considering that. So this is a way we have to identify whether the object has been inserted in the knapsack or not from the data present in the table. So see here, initially the profit is 7. So we were going from the 7. And I'm checking whether the same data 7 is present in the previous row. If it is present, then I'm going back. Even again, I'm checking it is present in the previous row, I'm going back. Again, I'm checking the 7 is present somewhere, no. Then the object 2 has been inserted. Okay, so whenever I take an object 2, the profit is 3 and the weight is 4. What is the remaining weight I have? 3. Sorry, remaining weight I have is 2. So I'll be going and checking in the place of 2 weight, that is obviously 3. So that means the first object. So when I add these two, the weight is also 5, the profit is 7. So I've got the maximum profit but the minimum weight, which means that when I add the weight of these two objects, that doesn't exceed the knapsack capacity. Finally, we have done with that. Yep. So we got the solution. And this is a running time. So when we identify the object has been inserted and when we compare the weight of each object, that takes big O of W time. And since we are repeating the same thing, then also we'll be getting big O of W. So it depends upon the number of items given in the knapsack. So the time complexity or the running time of this knapsack algorithm is big O of N into W. So when we see that's it, we have completed with the solving of knapsack problem using dynamic programming. And the last part is if we see the applications of knapsack problem or the areas and which places will be applying the knapsack problem concept is in the case of resource allocation with a financial constraint and using a construction and scoring of heterogeneous tests and using a selection of capital investment. In all these places, we'll be using applications of knapsack problem. That's it. Thank you for today's session. Thank you.